Welcome to the UEI Technical Masterclass. I hope everyone's doing well today and weathering this current pandemic. I'm Bob Finn with UEI, and today's webinar is entitled MIL-STD-1553, RTSA, Set and Read Data Words, and more. This is the last webinar in our month-long focus on avionics. In today's session, we'll continue to examine MIL-STD-1553, this time focusing on the remote terminal subaddress element of the system. Because of technical difficulties, today's webinar has been pre-recorded. However, our application engineering team is live, on hand, and eager to answer any questions you have about today's topic. So just send them using the webinar chat tool. And please don't be shy. So without further ado, I present today's webinar hosted by our own Phil Zavitas.
Welcome. Thank you for joining us for the 1553 Remote Terminal Masterclass. We're going to go over general 1553 concepts, the responsibilities of a remote terminal, how you verify a system meets specifications, and how you configure a specific channel on the I/O board. We'll be talking about RTSA memory, setting it and reading data from it, also checking to see if something was received or transmitted, as well as enabling and disabling RTSAs at runtime. And lastly, error injection. A typical 1553 system will have a bus controller, up to 32 RTs, and each RT will have 32 subaddresses. And there's an optional bus monitor that allows you to see what's going on the bus. The RT is responsible for handling commands. If it's a receive command, it needs to receive the data. If it's a transmit command, it needs to transmit its data, as well as other commands. It also needs to reply to commands with a status word so the bus controller knows whether there was an error. It also needs to comply with mode codes or mode commands, and the bus controller actually controls the RT itself with these commands. And then the remote terminal can optionally initiate a service request so the bus controller pays attention to it. Typical commands: the bus controller might send data to an RT, that's a BC to RT command, might be a firing command. The mission computer may need information from an instrument, that would be an RT to BC command. Or the bus controller may combine these two and have the instrument send another RT information. That's an RT to RT command. There are many one-to-one commands, maybe between a bus controller and an RT or between two RTs, as well as broadcast commands, a one-to-many relationship. A list of mode codes, and some of the things the bus controller may need the RT to do is initiate a self-test, shut down, things like that. There are several words in a 1553 system. There's the command, there's the data, and here is the status word. And the RT is responsible for returning the RT number and whether there was a message error once it receives a command. This is very important, and this is central to the reliability of a 1553 system. The SAE has developed an AS4111 test to verify that remote terminals, bus controllers, the 1553 systems conform to the specification. The UEI 1553 I/O board is actually two complete 1553 systems. There are two channels, and each channel could be a bus controller, an independent bus controller. Or one channel might be a bus controller and the other channel a remote terminal. There are many options here. Let's talk about enabling a channel to be RTSAs. There are two techniques. You can enable some of the RTs. So you might create a list with specific RTSAs, and you may have 5. So size would be 5, and this would be the list you want enabled. Or you can use 0 and null as arguments, and every RTSA in the system will be enabled. You can also dynamically disable and re-enable RTSAs at runtime to stress the system or to address dynamically changing simulations. You may need 5 RTSAs for one simulation and 22 for another. The handling of data words is central to running the system. Transmit data words are words sitting in RT memory that will be sent to the BC on an RT to BC command. Receive data words are the words the RT received from the bus controller. Now, questions come to mind. How do we read the memory? And how does the application know if the data words transmitted or data words were received? We have a technology called VMAP, which is a high-speed memory map technology that allows you to read and write RTSA memory. It's flexible and easy to set up. You set up a number of generic output channels, so they're not assigned to an RTSA yet. And you could have 3, 5, 50, and then you can set up generic input channels. And again, they're not assigned to an RTSA yet. At runtime, you request information from certain RTSAs. That would be the data it received. You also request to set the TX data, the data that will be sent to the BC. So you can read from RTSA memory or write to it. You can do either one, and these RTSAs do not have to match. And then one API call, DQADV VMAP refresh, sends all outputs, which is setting the transmit data memory, and reading all inputs, which is reading the data the RTSA received. Optionally, you can call refresh outputs and inputs individually. What can be read? Well, the 1553 specification says that you need to be able to read up to 32 data words. Our I/O board allows you to configure the read to add additional words at the beginning of the data, such as command and status, and command 1 and status 1. So this both would be used in an RT to RT command. In a BC to RT command, you would simply see the command here and the status returned from the RT, as well as the data words. You also have the option to add in the timestamp. So you would have 16 bits and 16 bits of the timestamp. It's a 32-bit timestamp. So let's take a look at a command sequence that would send data to RTSA memory. This is the receive data. So you would see on the bus a receive command. This is RT8, receive SA8, 4 words. You would see this hex value and then the data values, and it would go into receive memory. The RT then replies with status. For transmit command, you would see a transmit command come in to the RT, and then it would send status and the data words that's in the transmit memory. But how does the application know if the data in transmit memory was sent or if the data in the receive memory is new? Well, there are 2 techniques. There are individual bits available, data sent and data ready on an RTSA basis. So every RTSA will have its own status, and there's different techniques to read that. And I've referred to some of our sample code here. Or you can configure events that will notify your application asynchronously if any RTSA receives data or transmits data. There are different events. You can set up a receive event for one RTSA or both events for one RTSA. Let's see some videos. Many applications use UEI's 1553 I/O board to simulate some or all of the RTSAs in the system. This means the data may need to be written to and/or read from RTSA memory on a constant basis. For flexible, high-speed operations on RTSAs, UEI provides a streamlined technology called VMAP+. VMAP Plus allows you to point one or more VMAP channels to one or more RTSAs at any time. For example, if you're using RT3 SA6, just use one of the channels that you've already created to read and write the memory. Next time, the same channel can read any other RTSA in the system. You could create enough channels to read all the SAs in one RT, and then redirect the channels to read all the SAs in a different RT next time. Or you can create 100 channels and point them to different RTSAs on each read. A single API call, DQRT VMAP refresh, sends the output data and then reads the input data. So in one call, you can set the memory of many RTSAs for an RT to BC command, and then read the memory of many RTSAs to receive the data sent from a BC to RT command. So in summary, you can read and write a variable number of RTSAs at any time with one API call. UEI's 1553 I/O board emulates a bus controller, any or all RTSAs, and a bus monitor. Through our API, you can control these components, read and send data words, and even check status. Sometimes an application needs to be notified of something happening rather than checking for it. To accomplish this, we've implemented event notifications for the following commands and conditions. For instance, when an RTSA receives data, when an RTSA sends data, when a mode command is received, or even when a specific mode command is received. On the BC side, the application can be notified when a minor frame starts, and the IRQ event can notify the application when any or all commands have been sent. An example of this is to use the IRQ event on the last command in the minor frame. When the event is received, you'll know that every command in the minor frame has been sent. There are many more events available through our API. So now that we've seen some videos, let's run some code. I have here a sample that uses our TX FIFO bus controller to send commands. And I've decided to send commands to one RT, SA1 to SA9. And here is VMAP Plus. So we set up channels and we prepare the output, which is data to be put in TX memory, and we request input, which is data from RX memory, for all these RTSAs. We call refresh, and then we can just simply look at the data. Very few lines of code to do a lot. So let's run the system. So here we've sent the commands, and the data I'm sending is the RT number and the SA number. And then we run the VMAP code to receive it or read it out of the RT, and it should match. Let's actually go in and change the data that we're transmitting. So let's, instead of starting at 1, let's increment by 9. Here you have SA1, and it is incremented by 9. So this is the data words that were transmitted, and these are the data words that were received and read out of the RT. Let's do an example of events. We set up here the transmission of a receive command. And here is a transmit command. So as we take a look at the event handler, which is a thread. So here's the thread. And when we get the event, when an RT transmits data, will be in this code, and when an RT receives data, will be here. Let's run this. So what I'm sending is a receive command. You'll see this. This is the bus monitor data, and it indicates a receive command was sent. The event fired, and we have RT8, SA8, and 3 data words. Let's go in and send a transmit command. You can see here on the bus monitor data, it's a transmit command. The transmit event fired, and it says RT8, SA8, transmitted data. And we can also go in and change the number of data words. And then we can view the receive event as well once more. So you can see the event picked up the 8 data words that were in the bus monitor traffic. And it doesn't have to be one command only. We can run both, but I thought I'd start with that for clarity. So you can see the receive command went, the receive event occurred, the transmit command went, and the transmit event occurred. Now let's go over some error injection. Injecting errors helps test a system, and there are a few very important errors to consider first. Making your data early or late on the bus, having too many words or too few words, or a parity error. All this functionality is available in our sample 553 utils.c. We also have errors for the status word. So you have control over the bits in the status word. If you want to set the message error bit, you can. If you want to set the service request bit, you can. And you can also dynamically disable and re-enable RTSAs on the fly. You can remove an RTSA from the system. Let's see some videos and run some more software. The UEI 1553 I/O board supports all the major components of a 1553 system. We can simulate the correct timing, correct status, appropriate responses, parity, as well as correct word counts. And in a perfect world, everything does behave properly. An RT replies in the proper amount of time with the correct parity bit, you get a response on the correct side of the bus, and the proper amount of data is present. But when simulating a real-world situation, you have to be able to stress the system, test the edge conditions, and error handling capability of the electronics and personnel. UEI provides you the ability to do just that. You can use our 1553 I/O board to stop communications on one side of the bus or the other. Ensure that the reply from the RT is early. Ensure that the reply from an RT is late. Force the reply to be on the wrong side of the bus. Make sure the reply has too many or too few data words. Create a data parity error. create a status parity error. And finally, disable any RTSA in the system at runtime. Together with our ability to support all the 1553 components operating correctly, UEI's ability to inject errors ensures your mission's success. In our previous video on error injection, we mentioned that our MIL standard 1553 technology not only allows you to simulate aspects of a fully operational 1553 system, such as the bus controller, RTSAs, and bus monitor. It also allows you to inject errors into the bus traffic, such as timing and word count. Additionally, you can use our 1553 I/O board to inject errors into the status word by setting the appropriate error bits. You can use UEI's ability to run any of the major components of a 1553 system correctly and inject errors to ensure your mission success. So this is sample 553. It's from our sample set. It's free to download from our website. And I've added just a little bit of code from sample 553 utils to inject an error. So let's run without the error first. And what we see are 4 data words. And now I'm going to cause too many words to be on the bus. So this code will run, and this says too many words is the define. And here we go. We've added an extra data word to see what the bus controller will do. Likewise, we can do too few data words. And we removed a word. We can actually remove any response whatsoever from the RTSA. There, the commands are going out with no status reply. But let's show you that you can reset the system to its defaults at runtime. You don't have to restart. And there we have it. We put the system back in normal operation mode. Other errors you may want to inject are removing an RTSA, either to stress the system or to reconfigure a simulation dynamically. So let's run with everything normal. And now we will remove the RTSA by enabling this code. Again, commands are going out, but no status is coming back because the RTSA is inhibited. And if your application requires it, you can simply put them back in at any time. There you have it, a normal running system. And lastly, control over the status bits in the status word the RT sends back. First, the normal running system. And we see status is 4,000. And now let's set the message error bit. You can see it's now 4,400. And we were able to force the message error. You can also turn on any other bit. Let's do the service request bit. And now you see it's 4,100. So control over bus traffic, injecting errors in bus traffic, changing the status bits, and removing an RTSA completely is all available in sample 553 utils. So today we've shown the responsibilities of the RT, setting and reading RT memory with VMAP Plus, checking for status with or without asynchronous events, enabling and disabling RTSAs at runtime. We do support many languages and programming interfaces on our I/O boards: C, C++, LabVIEW, Simulink, Python, and many more. You can download the software I showed you today off our website at support/software downloads. And there's also a 1553 tutorial page available here. Thank you for coming today. If you have any questions at all, please send them in. If you'd like to contact us after this to go over software, techniques, or be pointed to certain samples to do certain things, I'd be glad to help you.
Okay, that concludes the pre-recorded part of our presentation. Our masterclass webinar host, Phil, is actually with us to answer the questions that you've sent in. So I'm going to turn this over to him now. Phil?
Hi, everyone. Thank you for your questions. One question came in. It says, does one channel support 32 RTs and 32 subaddresses per RT? Yes, it supports the entire set. You don't have to enable them all at any time, but they're all available if you wish to use them. Can events be used to check status on some RTSAs and the status bits be used for others? Absolutely. You can enable events on an RTSA basis. So if you need events for 2 RTSAs, you can do that and then use the status bits for the rest of the system. Can a bus monitor be added to the RT channels? Absolutely. There's sample code for this. It's very simple. It's about 3 or 4 lines of code to OR in a bus monitor and set it up. I'd be happy to email you that code. How can you self-test an I/O board? Well, sample 553 and our PowerDNA Explorer are all designed to use a loopback test adapter that comes with the system. So it ties channel 0 to channel 1. So you can set up one channel as a bus controller, the other channel as RTSAs, and run a complete system to verify an incoming board or to basically debug a system. You might be able to remove all the external wiring and see if the wiring is causing an issue in your fielded system. There's also power-up self-tests that occur. These tests are also available to your application to run at any time. Must I check for status to indicate there's new data before reading the RT? No, you don't have to. The facility's there to be used if you'd like to, but some applications simply continuously read the receive memory, and some will check for that status before they do it. How does the RT receive mode commands? Well, that's an interesting question. Subaddress 0 and subaddress 31 are dedicated subaddresses for mode codes. So that's how the system handles that. Can you run 4 sets of remote terminals? Yes, with each I/O board has 2 channels, so you would need 2 I/O boards. And you would have 4 completely independent sets of RTSAs. Well, can I upload a file through the RT to an external system? Yes, that's an excellent question. The bus, assuming an external bus controller is sending commands requesting data from the RT, you can simply put 32 words at a time in RTTX memory and the bus controller will obtain those and form the file on its end. And you would be continually feeding the RTTX memory until the entire file has been transmitted. In the first example, the data was the same to each RTSA. Is that a requirement? No, I apologize. I should have probably made each data word different, but there's no requirement whatsoever that the data be the same to each RTSA. That concludes the list of questions. Thank you for attending today. We're available. If you have any more, there'll be a slide at the end with our contact information, and please feel free to contact us.
Okay, great. Thank you, Phil. We'll be continuing our UEI Masterclass series at the same time next Thursday. Next week, we'll be taking a deep dive into using UEI hardware with OPC and Modbus. Another thing to note, we record every webinar and post the video online the same day. So you can also watch any of our previous sessions, including this particular one, either on our YouTube page or on our own webpage, ueidac.com/videos. And finally, we hope that you found this webinar useful and hope to see you again next week. We'll be contacting anyone with unanswered or partially answered questions. If you have any additional, if you need any additional support or you've got a suggestion for future webinar topics, please email us at support@ueidaq.com or call us at 508-921-4600. And thank you again for joining us.